All right, students, we're going to do a short video on how to draw a flow net. Some of you had some questions about that. So we wanted to generate a video so you could refer to this. And just make sure you remember all the rules and going through following the rules, you should be able to draw this fairly accurately and well. So what's the point of this? Well, obviously we want to look at how water is flowing through a layer or many layers of soil in seepage when we have a hydraulic gradient causing the movement of water to flow through the soil. As you can see in this image here, where you have water much higher on one side than the other, and that allows us to see the flow of water as it travels through this soil in this direction here, down to some sort of a filter, and then out at a level that we are wanting it to be. So let's recall what a flow net actually is. It is a family of two orthogonal curves, meaning that they are there's a family of curves that are perpendicular to each other. They consist of flow lines, which are the average lines of flow of water through the soil, the porous medium, from a high energy to a low energy, or upstream to downstream, and the equipotential lines that exist to show the change of energy as the water is flowing through that porous medium. They represent equal amounts of total head loss, and when they intersect with each other at right angles, creating this orthogonal grid system, they result in some what we call quasi-squares, which means that for the most part the grid boxes are about square shaped. They don't have to all be the same size, but they should be close to similar height and length distances. And then, of course, the rules are flow lines never intersect other flow lines, and equipotential lines never intersect equipotential lines. The rules are pretty simple and standard to follow on how to draw flow nets. First thing you want to do is have a good drawing of the scale of the overall system itself. So what you want to do is make sure that you understand where the soil medium exists, what all the boundary conditions look like as far as where the impervious layers are, or layers that are changing depending on the type of soil you're encountering. And at a convenient scale, typically you want this to be the same scale if you assume that the hydraulic conductivity is similar horizontally and vertically for the soil layer and that your water is seeping through. Then you want to identify any boundaries that exist that confine that flow. For instance, the water-soil interface is an equipotential line. Any impervious boundary, for instance, around a wall or along an impervious layer, that is going to represent a flow line. From there, you trial and error some intermediate flow lines between the flow lines that already existed based upon the boundary conditions that you saw. Then, once you have appropriate intermediate flow lines, then you create equipotential lines orthogonal to those flow lines to create quasi-squares. So let's go over an example of that now. All right, so we have here a weir wall, concrete wall of some kind, or a dam. We have the water level on the left side that is about 30 feet above the dredge line, or the soil water interface. And this weir wall has a sheet pile wall embedded at the toe of the wall itself. And on the right side, or the outflow or downstream, we have about 5 foot of water above where the ground surface is as far as the dredge line is concerned. So again, the rules were to first look at any soil water interface, and that becomes an equipotential line. This is one equipotential line. Here is another equipotential line. Now we look at any impervious surfaces, and those would be flow lines. So along the weir wall itself, we would have a flow line, and then around the sheet pile wall all the way to, look at this, an intersection here and here between a flow line and an equipotential line. We also have another flow line that exists along the impervious layer at the very base of the layer itself. Now that we have that, the next step in the procedure was to determine or to trial and error intermediate flow lines between these two flow lines that have already been drawn. So for this case here, obviously we want to start close to the other flow line here, but we want to make sure we are perpendicular to the equipotential line that already exists. So we'll here, work our way through and around, and again, perpendicular to the equipotential line. Now we need, that doesn't quite complete all of what we're dealing with here, so we'll do another one right here. Again, perpendicular to the equipotential line, and then maybe one more to kind of round this out here. All perpendicular to the equipotential lines that already exist. Now that we've completed flow lines, we want to draw in a grid system for equipotential lines that are perpendicular to these flow lines. So remember, they need to be perpendicular to all that exist, and you want to make somewhat squares here, so the similar distance vertically as horizontally. Distance here should be similar to this here. And it's okay to have a little bit, especially at the ends, it's a little bit difficult to have them perfect squares. Should work out okay. So I'll draw another one here, like so. There's another one. And you can see the distances between them need to be somewhat to where they create squares. Draw one like this here. There. Like so. And like that. That looks pretty good. So now, in this case, our delta H here is 25 feet. Our number of flow channels is 1, 2, 3, 4. Number of equipotential drops is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now let's look at this one here. This one looks a little more complex, but it really isn't too bad. What we like to do in this case is obviously following the same rules. You want to look at the water-soil interface here. One equipotential line there, and then also one across here. We also want to look at our impervious layers. We're going to have a flow line that goes around here, another around here, and then of course one all across the impervious surface at the very bottom where the rock is. Next, we want to look at intermediate flow lines that exist through here. And so what we want to do then is obviously we want this to be perpendicular in nature. And some of these can be a little tricky here. But we can see that we are perpendicular coming around like this. Till we get towards the center, we'll do the same thing on this side. It's looking fairly symmetric, right? That we want to have these as symmetric as possible. And I think what I'm going to do is do one more coming around like this. One more coming around like that. That looks pretty good. So now we fill in our equipotential lines from there. And these should be fairly easy when it comes to this. Again, creating quasi-squares, crossing at crossing where they become perpendicular in nature. And obviously this would be symmetric on both sides. Like so. Okay. All right, so now we have, this one's quite interesting because the number of drops and the number of flow channels, typically what we want to do is split this in half, right? So I would come through and cut it in half and just look at one side of this, and then multiply it by 2. So let's go ahead and look at the total head loss for this system here. Is going to be 8 meters, right? The 4 meters from here all the way down down to here, and then another 4 meters to get to this water level in the inside of that those two sheet piles. The number of flow channels here. So the number of flow channels would be, looking at just half of this system here. 1, 2, 3, 4, 5 flow channels in half the system, and then the number of equipotential drops is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So there's a way. There are 2 examples of how to draw flow nets for 2 different types of structures where seepage will exist.